Yeah. Today we are going to discuss that previous assignment 4 is the first question of the assignment 4. Determine the Norton current and resistance if R1 and R2 equal to 10 ohm and R3 equal to 20 ohm and I equal to 4 amps. This I is a current source. It is independent current source. It is having a rating of 4 amps. Then R1 and R2 equal to 10 ohm. This is 10 ohm and this is 10 ohm and R3 equal to 20 ohm. Okay. In the circuit, we need to find out that ISC, that is nothing but a Norton current, and RTH. Okay. First thing, when you are going to apply this Norton, yeah, when you are going to apply this Norton, is there any problem? Okay. Yeah, sorry. Just a minute. Yeah. When you are going to apply a Norton theorem, first you have to short circuit that load terminals, right? For that thing, I'm just erasing these values and I'm short circuiting the terminals of AB. Okay. If I'm short circuiting this one, then equivalent resistance will be zero, right? The equivalent resistance of the short circuit is zero. The 0 ohm is parallel with R3. So, what is the equivalent resistance of these two? That is R3 is parallel to that R. That is nothing but a 0 ohm, right? R3 here is 20, yeah, 20 into 0 by 20 plus 0, it is 0. Okay. Whether this resistor is placed here or not, it is not, it doesn't matter. Why? Because the short circuit path is across this thing, so the whole current, whatever the current coming from here, the total current is flowing through this terminal. I think there might be a delay. Okay, fine. So our new circuit is going to be this I and our R1 and our R2. This is point A and this is point B. Here our R1 I equal to, what is the value of I? It is 4 amperes, and that R1 equal to 10 ohm and R2 equal to 10 ohm. This is ISC or I need to, right? Then how to find out this thing? The current, so a current source, a two parallel resistors are connected. So we can apply current divider rule, right? Yeah, just give me a second. Now we can apply the current debit rule, right? What is the current debit rule? We want to find out this current through this branch. Okay, the current through this branch, let us suppose uh, ISC equal to total current, that is 4 amperes, into opposite resistance. What is the opposite resistance here? That is 10 ohm by total resistance, that is 10 plus 10. Okay, this is 4 into 10 by 20, that equal 10 ones are 10 twos are. The ISC is 2 amperes. I think there is a bandwidth problem. There is a delay in this class. Up to this point, this is clear, right? ISC. One can drop a text if you have any doubt in this thing. I hope till this point it is clear. I'm moving to the next one. That is the next step is we need to find RTH, right? Okay, we will move to next video. To find the RTH, first we have to make it this current source 0, right? To make this current source 0, when will the current source become 0? If you make it as short circuit, if you make it as a short circuit, the voltage across this short circuit is 0, right? If you make it as an open circuit, the current through this one is equal to 0, right? So to make this ideal current source 0, we have to open circuit here. That is, our new circuit will looks like this one only, that A, B, and R2 and R1, R3. So we want the resistance seen from these terminals, that is AB terminals, that is RTH. Okay, here this one is open circuit, so we can ignore this one. I'm erasing this part. Yeah. So here this R1 and R2 are connected in series. So what is the equivalent resistance? That equal to R1 plus R2, right? Those two are connected in series. The value of R1 and R2 equal to 10 ohm plus 10 ohm. So total resistance is 20 ohm. So the 20 ohm, yeah, this R1 plus R2, this equivalent resistance equal to 20 ohm. This is connected in series with in parallel with this R3, right? Now the equivalent circuit will be looks like this is R3, that is equal to 20 ohm, and our equivalent resistance just we calculated, that is 20 ohm. So the resistance seen from the AB terminals is, that is RTH. That RTH is, those two are connected in parallel, right? The 20 ohm and 20 ohm are connected in parallel. So the equivalent resistance will be 20 into 20 by 20 plus 20. That equal to 10 ohm, right? So that ISC equal to 2 amperes and RTH equal to 10 ohm. This is the Norton circuit. What is the equivalent circuit? This is the equivalent circuit, right? A and B. This equal to RTH. This equal to ISC. This is of RTH equal to 10 ohm and ISC equal to 2 amperes. That is 2 amperes and 10 ohm. That is option D. Okay. I hope this question is clear. If you have any doubt, you can drop it in a chat box, or you can unmute yourself and you can ask the question. I'm moving to the next question. Yeah, thank you, Amit. Okay, I'm moving to the next question. The question is, obtain the Norton current with respect to the terminals A and B for the following circuit. Just we saw that. What is the method to find out the Norton current? First, we have to make these two terminals short circuit. Okay, the Norton current is nothing but a short circuit current. That is, this is this is Norton current, right? Okay, now we, we short circuited the terminals of A and B. So what is the voltage across A and B? That is VAB. We short circuited those two terminals. So the voltage VAB equal to 0 volts, right? So the voltage at this point and at this point is this these are 0 volts, right? The volt potential difference across this point. So the Vx is same as VAB. That VAB equal to 0. So Vx is also 0. So Vx equal to VAB, that equal to 0. Okay. Then if Vx equal to 0, if Vx equal to 0, what is the value of this dependent current source to Vx? That equal 2 times of 0, it is 0. This is also 0 amperes. Okay. Here, this short circuit is across this 60 ohms, right? So, obviously, the current flowing through this 60 ohms is 0. Why? Because the current the the current always flows through minimum resistance path. That is this short circuit path is that minimum resistance path. So the current choose the path, the current up to this point, current comes to like this, and after this, the instead of going this side, it is showing the current is seeing the low resistance path from this side. So the current will goes through like this. Okay, therefore, yeah, yeah, obviously. Therefore, the total 30 volts is applied across this 12 ohm resistor. So, the current through this point is that IN is same as this circulating current, that is I in the loop, that equal to 30 volts by 12 ohm. That is simple from Ohm's law only. That equal to 30 by 12, which is of 2.5 amperes. Okay, that is option B. Yeah, that is option B. I hope this question is clear. We are moving to the next question, that is third one. The third question is, find the Norton's equivalent for the below circuit. Are you able to see the third question? So, yeah, just a minute, just a minute. Just a minute. Due to that network issue, it is disconnected.
Good, sir.
Yeah, up to third question it is clear, right? Up to second question it is clear. I'm starting the third question. Sorry for that thing. There is a network issue here. So due to that, there is a delay also during the video as well. So the third question is, find the Norton's equivalent for the below circuit. Not sorry, instead of Norton's equivalent here, find the Norton's equivalent resistance. Okay. Uh, yes. In this circuit, you have only the one independent source and two resistors. If you want to find out that Norton's equivalent resistance, you have to energize this independent source, then you have to find how much resistance offered by this network. Okay, to do the thing, yeah, to do that thing, just we are energizing the network, that is, yeah, I can draw here itself, it is better. I'm energizing this network with 1 volt source. Okay, now the voltage at this point, I consider this is as a reference. So the voltage at this point is 1 volt, right? Why? Because I'm applying here 1 volt. The 1 volt is applied across these two nodes, that is this node and this node. So straightforward, the voltage at this point equal to 1 volt. Therefore, the 1 volt is applied across these two resistors as well. So what is the current in this? Let us suppose this is loop 1. What is the current flowing in this loop 1? That equal to this voltage by total resistance, right? The total resistance here is this current. Let us suppose I, that I equal to total resistance, that equal to, let us suppose, sorry, the total voltage across, that is 1 volt, by total resistance, that equal to 10 ohm plus 20 ohm. Why? Because 10 ohm resistance and 20 ohm resistance are connected in series, so the equivalent resistance will be sum of those two resistors, so the current will be 1 by 30, that equal to 0.033, right? By 0.033 ampere. Okay, now what is the V naught? V naught in the circuit is the voltage across the, yeah, the voltage across this 20 ohm resistance. Okay, the V naught equal to the voltage across this 20 ohm resistor. We know the current through this 20 ohm resistor, that is 0.033 amp. We can find out this V naught, right? That V naught equal to, simply from Ohm's law, that equal to I into R. Here resistance R equal to, that is 20 ohm, and the current through this 20 ohm resistor is 0.033 amperes. So the voltage will be 20 into 0.033, that is 0.66 volts. Now we know this V naught. Then we can find out this 0.5 V naught, the current delivered by this dependent current source, that equal to the dependent current source is delivering 0.5 V naught, that 0.5 V naught equal to 0.5 into V naught equal to 0.66, or this value 0.6667 into 0.5, which is nothing but a 0.333 amperes. Okay, now we here, yeah, at this node we can apply KCL, right? That is the current, this current is flowing this direction and this current is flowing this direction. Let us consider that 1 volt source is delivering like this direction. Okay, I'm redrawing the same thing. This is considered I1. This equal to, let us I input from the 1 volt source, and this is one more current. What is the KCL at this node? The KCL equal to I in the entry currents plus that 0.5 V0 plus, sorry, equal to I1, right? Equal to I1. That is nothing but a incoming currents, that is I in plus 0.5 V0 are the incoming currents at this node, and this I1 is the outgoing current. So this I in, what is the value of I in plus, what is the value of 0.5 V0? That equal to 0.333. Just we calculated that value, 333 equal to I1. What is the value of I1? I1 just we calculated, that is nothing but is 0.033 amperes. 0.033 amperes. Okay. Then one can find out I in equal to 0.033 minus 0.33. So what is the value? Which is equal to minus 0.3. That I in equal to minus 0.3 amperes. So here we applied 1 volt voltage source, and this network, yeah, this complete network drawing a current of minus 0.33 amperes. Like this, it is drawing a current of minus 0.33 amperes, sorry, minus 0.03 amperes. So from the Ohm's law we can find out the resistance of this network, right? That is simply this voltage by the current, right? That equal to the resistance of the network equal to V by I, simply from Ohm's law. The voltage we applied is 1 volt. The current drawn from the 1 volt resistor, 1 volt source is minus 0.3 amperes. So the resistance will be 1 by 0.3, which is of minus 3.33 ohm. Okay, the resistance of the network is minus 3.33 ohm. That equal to option 1. I hope this question is clear. Moving to the next question. Anyone have any doubts? If you have any doubts, please drop in the comment box. I'm moving to the next question. Yeah. Next question. What is this question? Compute the value of R that results in maximum power transfer to the 10 ohm resistor. We have to consider this 10 ohm resistor as a load. We have to deliver maximum power to this 10 ohm resistor. And considering all are aware of this maximum power transfer theorem, that maximum power transfer theorem says that when I'm just present, okay. Yeah, the the maximum power transferred to the low, let us suppose this is, yeah, this is load resistance, this is the Thevenin's resistance, and this is the Thevenin's voltage source. Uh, the condition to deliver the maximum power to this load resistance, that will be RL equal to RTH, right? That load resistance should be equal to the Thevenin's resistance to get maximum power from the source, right? The same theorem we are applying here, that equal to deliver the maximum power to this 10 ohm resistor, we are considering this 10 ohm resistor as a load, and we are find outing the Thevenin's resistance seen from this 10 ohm resistor, and we are equating the both of these values to fulfill this condition. From that condition, we are going to find out the value of the resistor, right? First thing, to find out the Thevenin's resistance seen from this 10 ohm resistor. Okay, to find the Thevenin's resistance, first we have to make this sources should be zero, right? That means the voltage source should be replaced with short circuit, and the current source have to replace with open circuit. Yeah, open circuit. So here the two sources are voltage sources only. So just we are short circuiting the two sources, and I'm just redrawing the same circuit. That is, here instead of 12 volts, I short circuited that. Yeah, it's better to draw like this. And we are consider this 10 ohm resistor as a load. So I kept the load terminals as open. Why? Because we want to we want the resistance across these terminals. That's what Thevenin's resistance, fine. Yeah. So this 8 volt should be short circuited. Then this 20 ohms will comes at this point, that equal to, this is 20 ohm, and this is resistance R, and this is the resistance RTH. Okay, that, yeah, that the Thevenin's resistance, that RTH equal to this R ohm resistor, and this 20 ohm resistors are connected in parallel, right? So the Thevenin's resistance RTH should be equal to R parallel with 20 ohm, that equal to R into 20 by R plus 20, right? This is what our Thevenin's resistance. But the thing is, to fulfill the to deliver the maximum power to this load resistance, which is of 10 ohm, the Thevenin's resistance seen from this 10 ohm should be equal to the load resistance, which is of 10 ohm, right? Here, just we found out this RTH. Okay, here our RL equal to 10 ohm. Okay, to deliver the maximum power from VTH to this RL, the condition is RL equal to RTH. Here RL equal to 10 ohm, right? Then RTH is, just we found out, that equal to R into 20 by R plus 20. It should be equal to 10 ohm to deliver maximum power. Okay. Now you can simplify this thing, that equal to 20 R equal to 10 into R plus 20 that equal 20 or 10 or yeah equal 200, right? 20 r minus 10 r that equal to 200, 10 r equal to 200 and r equal to 20 ohm, right? This r should be equal to 20 ohm to deliver maximum power from these two sources to the resistance of 10 ohm resistor. So that option A is the correct answer. I hope this question is clear, right? Okay, there is no text chart window. Then we can move to the next question. The next question is determine the maximum power absorbed by the resistor connected across the terminal A and B for the circuits shown below. Okay. Here he connected one resistor which is RL. Determine the maximum power absorbed by this resistor. So the power absorbed by this resistor 0 PL. He is stating its maximum power, right? This is PL maximum. Okay. Just we saw that I am drawing the previous circuit only. Just okay. This is VTH. This is RTH. This is RL. The condition for the maximum power transfer is RTH equal to RL, right? So the current flowing through this loop is, let us suppose I. What is the value of I? I equal to VTH by RTH plus RL, right? Why? Because this RTH and RL are connected in series, so I added the RTH and RL. So the I equal here RTH and RL are same, right? The condition for the maximum power transfer theorem. So I can write this as VTH by 2 RTH. Why? Because I replaced this RL with RTH. So RTH plus RTH it will becomes 2 RTH. Right? 2 RTH resist is flowing, sorry, VTH by 2 RTH current is flowing through this RTH resistance and RL resistance. Okay. So the VTH voltage is applied across this RTH resistance and RL resistance. What is the voltage appeared across this load resistance? Let us consider VL. How can we find out this VL? We can find out this VL by applying voltage divider rule, right? That VL equal to total voltage that equal to VTH. Okay. Then that resistance that equal to RL by total resistance that equal to RL plus RTH, right? You can replace this RL equal to RTH from this maximum power transfer theorem condition that equal to VL into RTH by 2 RTH. This RTH and RTH will be cancelled, and VL, sorry, here it is not VL, it is VTH. Yeah. Now the VL equal to VTH by 2, right? You know the VL, and you know the current through, yeah, you know the voltage across this resistance, that is VL, and you know the current through this resistance, that is IL. You can find out the power, right? The power can be written as PL, yeah, I'm writing here, PL equal to VL into IL. I can write like this, right? So the VL equal to VTH by 2, and the IL equal to VTH by 2 RTH. So VTH into VTH, it will become VTH square by 2 into 2 RTH, it will become 4 RTH. So PL maximum equal to VTH square by 4 RTH square. So to identify this maximum power, we have to find out the Thevenin's resistance, that is RTH, across the terminals A and B, and you have to find out the Thevenin's voltage seen from this terminals A and B, right? For that thing, you have to find out VTH and RTH, right? That we first we will finding VTH, right? VTH is voltage across these terminals, the A and B. So here this, yeah, this is a closed loop, right? You can apply a KVL in this particular loop. Then let us suppose this current as I1, and I1, or you can simply directly apply the voltage divider rule as well. Yeah, we can go through voltage divider rule. It's, we want this V0, so you can apply this voltage divider rule. V0 equal to the total voltage, that is equal to 8 volts, into that resistance, that is 1 kilo ohm, by total resistance, that is 1 kilo ohm, plus 3 kilo ohm, right? I applied the total 8 volts is applying across these terminals, the 3 kilo ohm and 1 kilo ohm. So we can find out this V0 by applying voltage divider rule, right? So that equal to 8 into 1 by 1 plus 3, that is 4, that equal to 2 volts, right? At V0 equal to 2 volts. What is the value of 120 V0 then? If V0 equal to 2 volts, then this 120 V0 equal to 2 into 120, what is the value? Is 240 volts, right? The 240 volts is appear like this. Okay. Again, you can consider this loop like this. Okay. And you can apply the voltage divider like this. Then you can find out minus V minus VTH. Okay. Again, we are going to apply voltage divider rule from, that is minus VTH equal to 240 volts into that resistance, that is 40 kilo ohm by 40 kilo ohm plus 10 kilo ohm, which is of 240 into 40 kilo ohm by 50 kilo ohm, right? What's the value? 240 into 40 by 50, which is of 192 volts. So the VTH equal to minus 192 volts. Okay, we got the VTH. Now we have to find out the RTH. Yeah. To find out the RTH, this 8 volts have to make 0. That is, 8 volts should be short circuited. If this 8 volts is short circuited, then what is the current in this particular loop? It is 0 amps, right? If it is 0 amps, then what is this value of V 0? This is 0 volts. If V 0 is 0, then this dependent current source value is 0, that we can replace with short circuit. So the RTH is the resistance seen from these terminals. That RTH is the 10 kilo ohm and 40 kilo ohm are connected in parallel. The RTH is 10 kilo ohm and 40 kilo ohm, 40 kilo ohm are connected in parallel. So the equivalent resistance can be written as 10 into 40 by 10 plus 40, that equal to 10 into 40 by 10 plus 40, which is of 8 kilo ohm. So what is the formula for P max VTH square? The VTH is, just we calculated 192, VTH square 192 square by R 4 RTH, 4 into 8 kilo ohm, which is of 192 square, that is 36864, yeah, by 4 into 8 kilo ohm, which is 4 into 8000, equal to 1.152 watts. The maximum power is, PL maximum is 1.152 watt. That equal to option C, that is 1.15 watt. I hope this question is clear. To attain the maximum power, the RL, that load resistance, should be equal to the Thevenin's resistance. Okay. From this, we found out that maximum power PL condition, power PL maximum, that PL maximum equal to VTH square by 4 RTH. So we want VTH, the Thevenin's resistance, and we want that RTH, the Thevenin's voltage and Thevenin's resistance. First, initially we found out this Thevenin's voltage here, that is, which is of minus 192 volts, and we found out the Thevenin's resistance here, which is of 8 kilo ohm. So from this Pmax VTH square by 4 RTH, we found out this maximum power, which is of 1.152 kilo, 1.152 watts. I hope this is clear. Yeah, these all lectures are available at a basic electrical circuit YouTube channel, and in the YouTube channel itself the notes is also available. I can show that thing. Just a minute. Yeah, I can I can present the screen, right? Yeah, and this screen. Yeah, you can access the videos, and you can access the notes as well. The notes is also available here. Uh, yeah, the notes is also available here. You I think you are able to see the screen, right? Yeah. The notes is available here. You can download the notes as well. If you want step by step solutions, you can able to download from here. Okay. Thank you everyone. If you have any doubts, so you can drop it in a chat box. Yeah, Lokesh. Thank you, Lokesh. Thank you. That's it for today's class. Thank you.